All this is a simple transmission line model, right? Which is given by a resistor and inductor in series, and then the conductance and the capacitor in parallel. Right? This is how electrically a transmission line can be represented. Now, the biggest discussion or biggest doubt, the high speed design engineers, or basically the guys transitioning from low speed designs to high speed designs, have is, when should we apply high speed design principles, or when should we treat a PCB as this transmission line, PCB conductor or PCB trace as this transmission line. That is the biggest question, right? Generally, PCB design engineers or electrical engineers who have worked on low speed designs, some of the people doesn't even bother about the return path also. Some of the people just use as much length of the trace as possible without applying basic principles. So still the PCB works, right? A professional designer generally applies all the principles, but guys who started working on PCB, or some of the guys who hobbies, for example, just lay out a PCB, right? Now, the question that we are talking about, when should we treat that particular trace as a transmission line and start applying all the high speed design principles, is understood by a simple formula. Okay, let us look at the formula. So here is a simple formula to determine whether the PCB trace acts as a transmission line or not. So the formula is basically square root of inductance per unit length into capacitance per unit length, and the square root of that particular product must be greater than or equal to rise time by 2. This is the signal rise time which we are actually transmitting. So if this condition gets satisfied, this particular PCB trace should consider all the um, rules, high speed design rules that are there, or PCB designer should consider this as a transmission line. Okay, now the first question comes to the designer. How can I know inductance per unit length or capacitance per unit length? So this is actually known over a period of time, and then how much width you are routing the trace, how much long you are routing the trace. Based on that, you can come up with the L and C values. Like this is a very typical thing. Okay, and this is only known by experience, and specifically rise time, we all know, is the rise time of the signal that comes out of the driver. Now, in our scenario, we have assumed that capacitance per unit length is 1 pf, inductance per unit length is 1 nanohenry, and what we did is we calculated the total propagation delay, which is in picoseconds. Okay, and then the rise time we have considered 1. Like here, if we consider a rise time of 50, okay, propagation delay is still greater. If we consider rise time of 100 nanoseconds, that means the signal is getting slower, right? The rise time is getting slower means signal is getting slower, and we are slowly getting into the low frequency design. And you can see here, it turned red. That means the transmission line, you need not consider this as a transmission line. You can route it without using the high speed design rules. You can treat this as a low speed signal, and if the signal rise time of the signal is changed, you can see here, now we have to consider. So this is the simplest formula. Okay, and one important principle which the designers have to know is square root of LC. Okay, this actually represents the propagation delay of a PCB trace. So It is known as TPD, propagation delay. Okay, propagation delay you can get to know from your PCB calculations, and then use this formula, and you can get to know whether that is a high speed signal or not. Hope we gave some glimpse of how this can be calculated. Please post if you have any questions. Thank you.